email, and it doesn't have that. Yeah. Right. Right. Okay. Fifth conceptual block of stuff, previously known as fifth week. Thanks for the people that let me know that the slides were irritating. I have, I think, put up PDFs that are well, black and white, perhaps a bit easier to read. Let me know if they're useful to you. I will try and compress everything down into shorter one document. Promise I'll get that done soon. So that's fifth week, and I've also already put up the next conceptual block of stuff that would have been sixth week if there, so you can go ahead. Where were we? Fly through this, and then there's a little bit at the end, and then I'm a bit torn between the two more blocks of stuff I want in order to do them. So how actual 3D crystals work, we had some definitions. We had lattice, bunch of points defined by the ends of arrows. You've got these sets of arrows, we call them lattice vectors. You can only have a lattice point at the end of an arrow. You can't shrink or grow the arrows, you can count integer numbers of them. The unit cell, you pick a couple of these lattice vectors, multiples of them or whatever you can find. The unit cell is the bit that you tessellate together, get all the space. Primitive unit cell is a unit cell that contains only a single lattice point, and I mentioned yesterday, if you've got something that's on the corner or of an edge, or I suppose a vertex or a face in 3D, you share the lattice point evenly. So in 2 dimensions, if you're sharing a corner, it's probably between 4 cells, so you get a quarter away from that. This Vigorous sites bit I should probably show you at some point, but yeah. But the lattice point, and on each lattice point you put a basis, and then you've got the actual cell. Why do we have this lattice and the basis? It allows a systematic reconstruction instead of just having a sort of, there's every type of crystal in the world, you know, but we can't make anything of it. There's just all sorts of them that you can find. In 3 dimensions with a lattice, there's only 14 allowable types that you can form by specifying 3 lattice vectors that aren't linearly dependent. Get these 14 types of lattice. Starting out, cubic ones where each of the 3 lattice vectors are orthogonal to each other. Different types of cubic one. These are no longer primitive cells, they contain more than one lattice point. You've got a cubic cell, you can put an extra lattice point in the centre, that's so-called body-centered cubic, or you can put an extra lattice point on each face. For this body-centered cubic one will actually have 2 lattice points in it. You get one lattice point that's in the middle, that's not shared with any other cube. Each of the 8 corners is shared with 3 8 cubes. Got 4 cubes down the bottom, 4 up. So when I get 1, 2, 2 lattice points in that one, and there's 4 before. Yeah, and 4 in the face sim. So six faces, and they're between 2 cubes. Faces get half, so 6 is 3, and then 1 on each of the corners as well, so 8. And then you get less symmetry than cubic. You've got octagonal, where one of the is different. You've got orthorhombic, where all 3 lengths of the vectors are different at a certain 90 degrees, and then you start tilting more and more away from them. The logical structure is that encompasses every type of lattice that you can possibly construct in 3 dimensions. So rather than having sort of an infinite variety of crystals, if you like, there's just 14 lattices. As we'll see a bit later on, if you do X-ray diffraction experiments, you can determine what lattice it is, which tells you quite a lot about the sort of underlying structure of the crystal and how it's periodically built up. And then onto each lattice point, you then hang some atoms, and then you get a real 3-dimensional crystal. So systematically, how you come up with all these things, use group theory from all your friends doing algebra, maybe doing next year. So you have to study, at least the practical elements, really, how objects change when you perform some sort of operation on them. It could be symmetry operations where you do reflections or translation, study how things change. We kind of implicitly did that last week when we looked at the crystal chain, and we said that the system shouldn't be changing if we move our coordinate system along by one of the atoms. If we move our coordinate system by A, everything should basically stay the same. And this allowed us to get this sort of Fourier transform, Fourier series expansion wave function. We specified which values of our wave vector should be allowed that allowed the thing to join up. That was really a sort of a manifestation of this idea that things shouldn't change when we use the symmetry of the crystal. So there's a whole bunch of stuff. You may see it later on. I don't know, did Matt talk to you about Noether's theorem? Yeah, so in Lagrangian, you get this conserved quantities where you have some symmetry. So you have the fact that you have this translation. So in real space, you can just move anywhere and everything looks the same. So that gives you this conservation of momentum. Rotations give you that. So in this case, when we're in 3D, we can't make we can't just move an infinitesimal amount, but we can move a discrete jump A. So we can move one of the crystal translations, one of these lattice vectors. And that gives this sort of K vector, which is a bit more vector. Seen in the book. But these yeah. So real crystals, if you go on Interweb and try and find the structure of, say, sodium chloride, say it's face-centered cubic, so it's one of those with a cube, lattice points on the corners and on the faces, and at each of the lattice points, put one of the atoms at 0, 0, 0, and another one at half the cell dimensions along the diagonal, and that builds up this sodium chloride structure. And I put a link to a website. Some molecular sponges, that sort of thing. See what they look like. So reciprocal space. So what I was saying is connected to the real space lattice. There's another. Again, so it's comes from this symmetry, this statement I've got here, that the wave vector that has something that changes by 2 pi when you get along by A. Getting the electronic structure of a crystal. That's one of these sort of translational things. So we're saying that things stay the same when we do that. So let's motivate this to generate this reciprocal lattice. Now, the bit at the end of the lecture, guys, we do last week and I'll do now. Yesterday. Allowed us to define, as well as this real space lattice, which is made up by putting together these lattice vector, these arrows, integer numbers of them, to define this lattice of n position arrows. We then hang atoms on crystal. We could define another lattice. It's these set of G vectors that are related to the real space lattice by this relation. Spent a little bit of time yesterday finding it. Essentially, if we've got real space vectors A1, A2 and A3 for our system, then we can define reciprocal space vectors, reciprocal lattice vectors there, satisfy this criteria, so they're orthogonal 90 degrees to the real space ones by doing this. This thing at the bottom is actually the volume of our cell. A little thing. So let's see why not. So that's the volume of our cell, and then this thing always generates something that's perpendicular to that. Go there. So there's a recipe to get these vectors. So there's a recipe to generate the individual reciprocal lattice vectors, and then we build up our G's from the integer multiples of the reciprocal lattice vectors. Now, why do we want to do that? Well, one case, essentially, this transformation to reciprocal space using this other thing related to the Fourier transform, like a wavelength or frequency representation of the position, is that lots of measurements are easier for crystals. I said that, but let's think how this case. I did a little bit of a talk briefly yesterday about, okay, before we look at reciprocal space, how can we look in real space? But now let's carry on. Let's work with reciprocal space and see why that is what we measure in X-ray diffraction. So next week I'll give a more detailed version of this, but this is just a quick motivator. So, we want to measure a crystal. This was one of the first things that was done that pretty much unambiguously proved the sort of atomic structure of nature. Using this property that crystalline matter repeats. As soon as you've got this repetition, which gives you this lattice vectors, which gives you this reciprocal lattice thing. So the gaps between atoms of the order of an angstrom or an angstrom. So if we want to be able to measure distances in a crystal, we need to use some measuring stick that is got measurements on the order of angstroms, which means we need a wavelength of the order of nanometers. And if we look at the electromagnetic spectrum, we see that X-rays have got a wavelength around about that. This is what was thought in turn of the beginning of the 20th century. Let's try shining X-rays at materials. It's bound to do something interesting. Essentially, the idea is to use the crystal as a diffraction grating for X-ray light. In the same way you had that Michelson interferometer or whatever you did in labs, and you could measure the spacing from the diffraction, the maximum in the diffraction peaks. You could tell how far apart this diffraction grating was with some sort of ordinary visual light. And we'll use a crystal, treat that as a diffraction grating, shine X-rays at it, and be able to determine from the positions of the maxima how far apart the atoms are. It's rather more complicated than that, but what we'll do now is just see how the typical lattice would allow us to get expected maximum and minimum pattern for X-ray diffraction. So the Bragg condition, I think most of you have seen kind of this sort of diagram before. You've got two planes of stuff. In our case, it's going to be planes of atoms. Imagine things that one be kind of replicated crystalline structure, and there's some distance here. B represents some crystal planes in material. If we have two light rays, two photons coming in, one getting reflected from this ray, from this row, and one getting reflected from this row, we can work out the total change in path for the two different ones that have gone a different distance. And the condition for constructive interference is that should be some multiple of the wavelength of the light that we're shining. That's sort of a level. Now, let me go back to this. All the wrong. What will give me a nice picture? So if we pick some sort of generic crystal, you can find lots of different orientations that give you lots of different types of diffraction rating. Depending on which angle you look at, it's a whole bunch of different rows. And better with a simpler crystal. So the point is, we've got this picture, but the D could be any all the different orientations of the crystal. All those could be different rows in there. So there's effectively a crystal acts like a whole bunch of diffraction gratings with different sizes of the grating. It's a whole collection of different D values. And we could guess what the crystal is, write out all these distances by reorientating and looking at all this stuff. But that would be quite a fiddly way of doing it. And what I want to try and show in a second, and this is basically it, is that in fact we've already done it. That what we have to do, we can just feed off the different fraction gratings in our crystal by taking 2 pi and dividing by the length of the reciprocal lattice vector. One argument for why the reciprocal lattice vector is called a reciprocal lattice vector is you've got units of 1 over length. This is kind of, I don't know if you remember, I had a real space vector times this reciprocal lattice vector is equal to 2 pi or some relation. So they're kind of real space vectors are dimensions of length. Reciprocal lattice vectors got dimensions 1 over. So 1 over the length of this is 1 over length. So it does now be a length. So jumping around a little bit, but what we had was a recipe for how to get a lattice from the lattice vectors. There's only 14 types. There's only a few types. So there's only a few types of lattice vector, and then there's a recipe to construct the reciprocal lattice vector for a crystal that had that lattice. So from that, we can construct the different lengths of the reciprocal lattice vectors. So therefore, we can turn in all the different types of diffraction grating that we have for our crystal. So then you can sit down and you can write out which angles you would expect maxima to appear from. And then so you can shine X-rays at it, see what pattern of maxima you get, and use that to kind of fingerprint whether you've got the right type of crystal. So where does this formula come from? This is, what I want to do is just a sort of a very quick ad hoc kind of derivation of that set of distances. So next week I'll do it a bit more properly, which may or may not be more informative. So the aim of this is just to sort of motivate that statement that once we've got the lattice vectors, we've got all the reciprocal lattice vectors, so we know all the different possible fraction grating widths for our material. This is how we go. So our definition of reciprocal lattice vector was this formula. When we take the dot product of a reciprocal lattice vector, any one of them, with a reciprocal lattice vector, any one of them, we get some integer multiple of 2 pi. Yeah, that was how we defined it. So okay. Now that basically the equation of a plane. We want to look at it a different way. There was one way of defining a plane geometry or whatever was to define what the normal is and then see which planes or which vectors are orthogonal or not to that plane. Fresh, I want to get it up. There's several different ways of defining a plane, but probably a bit clearer. Oh. I'll put a link in. I can't remember quite what's here. Not checked it's live either. Just off Tinterweb, you can check that. It's the different ways of defining a plane. But basically, you've got a normal, and then you dot product with any other point, and then you can figure out whether it's in the plane or not. So, distance from the plane, most of the plane. Distance class. So, if we've got that formula, if we have any 2 points separated by one of our lattice vectors, got 2 planes called Rn plus 1 and Rn. 2 points in those planes. So going back, so essentially this is Rn plus 1 here, this is Rn down. We've got 2 planes and I'm connecting them by 1/5 of the lattice vector from here to. So I've got the distance between, a vector difference between my 2 planes, my Rn plus 1 minus Rn. That's the vector that takes me from the first plane to the second plane. If I dot either of them with the reciprocal lattice vector G, I get some multiple of 2 pi. So let's say that for these 3 connected ones, I'm going to get 2 pi. Each of those dots is going to give some multiple of 2 pi. Let's take the close. Okay. Now, the other expression for a dot product is you take the dot product of 2 vectors. The other formula for it is the length of vector 1 times the length of vector 2 times the cosine of the angle between the 2 vectors. So dot product, subtract it's one mark either. So we can do your sort of component-wise one, but the length of the dot product of A and B, the length of A times the length of B times cos theta. So here I've got G, which is my first vector. My second vector is the difference between these 2 vectors, which is D. That's the distance I want between the 2 planes. And so if I work perpendicular to G, so if I'm working, if G is the normal vector there, then cosine is 1, and I'm just left with difference between the planes is 2 pi divided by the length of this G vector, which is what I wanted to prove in the first place. There's a few more subtleties, whether or not this G vector is unique, that or not. But if you pick the smallest one, and it will always give you one of these. Have a look in the textbooks for a picture to make yourself happy with rise planes, if you like. But the idea is, instead of going through drawing out a crystal or making a model of it and turning it around, looking at each of the different ways of drawing a plane through it, measuring the distances and so on, all of these possible distances, all these possible diffraction grating widths are actually encoded in this reciprocal lattice vector. And in fact, I sort of mentioned it when I this thing about the real space and we've got the surfaces. There's something called a Miller indices, named after William Miller or something. So if you've got these reciprocal lattice vectors, build any given reciprocal lattice vector by taking integer multiples of these reciprocal lattice vectors. And these H, K and L, for the same kind of reason I mentioned before, basically define a normal to a plane of atoms in the crystal. So when I thought about these surface measurements, and I talked about I've got my crystal, I orientate it in some way, and then I make a cut. So I've got, so this gives you a better idea of the planes in the crystal back. I've got a plane here and a plane here. I've turned it round at some angle, so there's some normal direction, and back to that equation of plane. So this will be one of the reciprocal lattices. Lattice vectors will kind of be that normal. So we can label our surface directions or the normals to a surface by which reciprocal lattice vector we're dealing with. We've got a certain number of reciprocal lattice 1, a certain number of reciprocal lattice 2. And actually this is called the Miller indices, and it's just written with brackets and 3 integers, which are the and they're also the normal vector to the surface that you're looking at. Where do I steal this from? So you get these different planes, different ones, and what they kind of tell you is about, so it's back to this definition of normal, and they tell you where the planes will cut the different axes. So again, this is just sort of geometry. So the 1, 0, 0, 1 cuts the x-axis at 1, but it never cuts the y or z axis. So it's a plane that's parallel to the x and parallel to the y and z. But you can see the same for the others, the permutations. And then you've got this 1, 1, 0. So it's going to be this 0. It's going to be parallel to the z direction. So it never cuts the z direction, but it cuts the x and y planes at 1. And if I have the -1, so this 1 bar means 1 here. Then it's orientated and it cuts the other axis, so they've rotated 90 degrees. And if I've got 1, 1, 1, it cuts the x, y and z. plane at 1, get this diagonal. So you can see this defines like another type of diffraction grating, these different types of, so each of these indices provides a sort of a family of these diffraction gratings. Seeing these geometrically and began to draw them out quickly is quite a art for you, but you can just write them out using simple lattice vector sort of mechanically without any sort of intervention there. There's higher index planes, and what you find in the end, again this is kind of the definition of the normal vector, is that the planes cut to the relevant axes at A divided by the index in that direction. So for those ones I showed, the 1, 0, 0 cuts the x-axis at A 0 at A, because gate 1, 0, 1, but it cuts the next one at 0 at A divided by 0, so at infinity, so it never cuts the other coordinates at which it cuts the axes given by the relevant lattice vector divided by the index. And that allows you to draw up these different families of vectors. So I'll try and get some nice pretty pictures and even some suggested ways where you can get some models up to have a play around and have a look at. But that's the 3D geometry of crystals. Real space, lattices, only a very limited number, 14 of them systematically come up with in real space. There's no other way, like tessellating structures in 3D, there's only so many ways you can do it. So you can write out a list of these things. And then you say, okay, if I look at these lattice points and turn them around in 3D and see which rows of them, which of those could act as diffraction gratings for X-rays, well, we can extract that geometric figure from this idea of this reciprocal lattice vector. So this is how the X-ray diffraction measurements work, or it's an essential element of it. But there's also a whole bunch of other scattering techniques where you chuck, neutrons, where you do various other types of measurements on crystals, and what you measure are these reciprocal lattice vectors, or these k vectors of the wave function, often referred to as working in reciprocal space or momentum space, because it's like this Fourier series or Fourier transform of the positions, but related on the symmetry operations of the crystal. Okay. I don't start streaming.